Welcome back. So far, we have tried to model knowledge graphs as SRO triples, where R can be any general relation. The only property of R which has mildly interested us so far is the matter of symmetry or asymmetry or antisymmetry. However, another very important property of R is whether the relation is transitive or not. What's a transitive relation? If person 1 is an ancestor of person 2 and person 2 is an ancestor of person 3, then person 1 is an ancestor of person 3 directly. That's a transitive relation. Or if a camel is a mammal and every mammal is an animal, then a camel is an animal. If Einstein was a physicist and every physicist is a scientist, then Einstein was a scientist. This defines type hierarchies in the knowledge graph. For the purpose of question answering, as well as interfacing to large language models, understanding type hierarchies in a knowledge graph is very important. So now we are going to look at how hierarchical relations can be modeled in a knowledge graph. So if camel is a mammal and mammal is an animal, then camel is an animal. And this might be useful if you are asking a query like deserts are home to which animals. The word animal may not even appear in an answer document. The document might just say that camels are called the sheep of the desert because they are used for transportation and food, right? And you know that that passage answers this question only if you know that camel is an animal from a knowledge graph. There are many popular type hierarchies like this in all the major knowledge graphs, but people have cleaned up bits and pieces of them and separated them out for individual experimentation. Feiger and the Google Find Type systems were some of the early type hierarchies with about 100 types in them, whereas DBpedia has about 700 types in it, and TypeNet, which is partly pictured in this slide, has approximately 1,000 types in it. Generally speaking, the type hierarchy is a directed acyclic graph and not always a tree. Nodes may merge from multiple parents as well as fan out from ancestor types. The root type here is all entities in the world, whereas more fine types such as fluid or station, broadcasting station, communication systems, a liquid can be a beverage, which can be a food or nutrient, those would be finer and finer types under the hierarchy. So one question is, the techniques we have learned so far, translation, rotation and factorization, are they really adequate at capturing hierarchical information like this? And the answer seems to be no, that we need separate kinds of techniques to explicitly capture the representation of hierarchical nodes or entities or types in the knowledge graph. There are at least two views of embedding hierarchies like this. One is to embed a hierarchy or a directed acyclic graph in a space that is still basically Euclidean. So we would like to have some notion of a distance in this space such that the distances in the DAG are approximately preserved by distances in the embedding space. And we will see a sequence of techniques in that style of work. Now, inherently this is a bit complicated because if you think about, say, a full binary tree where one node fans out to two nodes and then those fan out to two nodes each and so on and so forth, within very few levels you have an exponential number of leaves, and you still want to make sure that this parent, say node 3, is closest to 4, 5 and 2 compared to all the other nodes. For that, you have to make sure that those Euclidean distances are very large compared to the distance between 3 and 4. This means you need a lot of space near the leaves to embed the tree properly, and that could be a problem. So the other option is to not really go after Euclidean distance in the embedding space. We can say that the embedding space doesn't care about Euclidean similarity. All it cares about is whether we can check the ancestor-descendant relationship efficiently using the embedding in the target space. Apart from this, these embeddings should work with incomplete supervision, because just like any other relation, the containment, type containment relation will not be complete in any knowledge graph. So it should work with incomplete supervision well, and it should also cooperate with other embeddings such as that we get from words. The embedding we are going to discuss just now, they don't directly support this working well with other word embeddings, but as we get back toward large language models, we will highlight some techniques to bring these worlds together and to align the topological world of the type hierarchy graph with the textual world of the corpus. Let's start with a brief review without any proofs of the theoretical results known, which show that low distortion embeddings may be quite difficult in the sense of Euclidean distance distortion. Suppose a graph G, which is characterized by nodes V and edges E, has a single node like small v, and that node is embedded to a vector x of v in d dimensions in some Euclidean space. The graph distance between u and v is called d sub g of u and v. For example, this could be the shortest path distance. In case of a tree, that would mean the path through the closest ancestor or in a DAG. The distortion of this embedding G or embedding with respect to the graph G will be given by this quantity. It will have a numerator and a denominator. The numerator is the maximum over all pairs of nodes in G of the distance in the embedding space divided by the distance in the graph space, and we take the max in the numerator. In the denominator, we still have the embedding distance divided by the graph distance, but this time we take the min. The larger this quantity is, the more distortion we have in the embedding, and this is fairly intuitive. Also, the hardness of embedding a graph G in general would be the smallest distortion I can get with regard to any embedding scheme. So, you could think of X as providing an embedding scheme for all the nodes in the graph. And no matter how smartly we choose X, the embedding scheme, we are going to get a distortion of at least this quantity, the infimum over X, the distortion of X with regard to G. Now, from the domain of Euclidean embeddings, the following facts are known about distortion. If you allow the Euclidean space, the target space, to have as many dimensions as you need, D can be arbitrarily large, then any graph with n nodes can be embedded with order log n distortion. If the graph is also known to be planar, that is, it can be drawn on a plane surface without edges crossing over, then it can be embedded in R squared in only 2D space with order n distortion. Trees can be embedded with order square root n distortion. With large enough dimensionality D, any tree can be embedded in R to the D with order log n distortion. Binary trees can be embedded in a line with order n over log n distortion, and in R to the D with order n to the 1 over D to over log n distortion. Distortion of a multiplicative error of 1 plus epsilon is not possible in any of the bullets so far, but it is possible in hyperbolic space, not in Euclidean space. So, hyperbolic space therefore has a lot of interest, and we will see a few slides about them a few slides down in this segment. So, how does hyperbolic embedding work? We have to first define the hyperbolic arc cos or inverse cosine of A, which is defined as the natural log of A plus square root of A squared plus 1. That graph is shown in this chart over here. Now, we will embed all points like x and y strictly inside the unit circle. And in there, the hyperbolic distance between x and y will be defined as the hyperbolic arc cosine of 1 plus twice. This looks like the Euclidean distance, but it is normalized with two terms. 1 minus the square of the norm of x and times 1 minus the square norm of y. Okay. It can be shown that basically we measure the distance between x and y not as this straight line, but along the geodesic following this hyperbola. So, as x and y approach the perimeter of the unit circle, the norm of x tends to 1 or the norm of y tends to 1. Therefore, these terms go to 0 and the hyperbolic distance goes to infinity. This is a very nice cheap fix. It basically says that looking at this disk from the Euclidean point of view, it has finite perimeter. However, looking at it from the point of view of hyperbolic space, it has infinite perimeter. Because the unit disk in Euclidean space has infinite perimeter in hyperbolic space, we can now easily embed trees in it. And remember that the motivation for embedding hierarchies comes from type hierarchies, which are mostly trees. So, hyperbolic disks provide a very natural way to embed trees, but there is a caveat that mathematically it may seem like the periphery is infinite in hyperbolic space. In a computer representation, nothing is really infinite in the sense of real numbers, and therefore, these precision bits used to embed these entities is not really free. We still have to encode everything with regard to finite bits of precision in a computer. That plus hyperbolic embeddings don't really play that well with the kind of word embeddings or entity embeddings from the earlier embedding strategies. For this reason, work on hyperbolic embeddings started out with a bang, but not too much happened about it, particularly with regard to its integration into language models and other embedding systems. However, that doesn't stop us from embedding large type hierarchies like WordNet, which has at least 15,000 types, into hyperbolic spaces. And we can get very nice diagrams like this, where the root of the noun hierarchy of WordNet, which is all entities, is at the center, and then more constrained and specific types appear near the periphery of the disk, such as mathematician, and Gauss was a mathematician, herb, so a herb is a plant, a scientist is a person, a mathematician is a scientist, a person is an organism, and so on. Right? Animal to mammal to sperm whale, matter to food to bread and pretzel, etc. So, it is pretty natural. However, remember that our driving application was question answering. Suppose we want to answer a question like scientists who played musical instruments or mammals that live in the desert, right? So, in that case, the Euclidean distance from camel to entity or to animal is not as important as whether camel appears in the subtree of animal or mammal. So, the real test we need is whether something is in the subtree of something else, not their Euclidean distance. To that end, we will now discuss a different approach to it. So, computing Euclidean or hyperbolic distance between items or nodes is not the only choice. We make up some notation. Suppose the partial order x precedes y means x is a descendant of y. In case of a tree, such as the one shown in this slide, we can associate with every item such as x two numbers. We start the traversal at the root a, we enter a at time 1, we enter b at time 2, we exit b at time 3, we enter c at time 4, we enter d at time 5, we leave d at time 6, we enter e at time 7, leave e at time 8, leave c at time 9, leave a at time 10. This is called an in-order traversal, and it gives every item x an interval I of x. So, let us plot it on a number line. Our interval a will now occupy the interval from 1 through 10, that is our a. Under it, b will occupy the interval 2 to 3, but c will occupy the interval 4 through 9. Okay. You see what is going on. To test if x is a descendant of y, all we need to do is to test whether the I of x is contained in the I of y. If the interval containment holds, then the ancestor-descendant property also holds. This is also a kind of embedding. It does not involve distances. It only involves comparing the endpoints and testing for interval containment. So, that means that if we did not care about Euclidean distance, nodes of a tree can be embedded in just one dimension to answer ancestor-descendant queries in constant time. Once I have found this in-order traversal numbers for every node and I store it as an embedding, if you later ask me, is this node an ancestor of that node or a descendant of this node, I can answer that by just comparing two pairs of numbers in constant time. This can be generalized from a single number line to multiple dimensions. And the corresponding concept there is vector dominance. For example, people can be represented by this particular apex marked by the red dot, and every point which has its x or y coordinate greater than that apex is supposed to be a person or an instance of people. So, x is a descendant, right? X is preceding y if the vector of x dominates the vector of y. For example, I could say that since all actors are people, the apex of actor has to dominate the apex of people. So, u of actor has to dominate u of people element wise. Every element has to be at least as large as the apex of the superset. Okay. Politicians will form another such open cone whose apex would generally be different from people and actors. And then some elements may be shared between actors and politicians, such as Arnold Schwarzenegger. Now, using this intuition, we have to design a training loss function. Why training? What we will be doing is, every type will be mapped to this apex vector, which would be the variable of the optimization. If x is a subtype of y, like actor is a subtype of people, I would like actor to dominate people, right? Which means I take u of people and I subtract u of actor. Okay? What should happen? If I take u of y minus u of x, since u of x is always larger, this difference should always be 0. If it is successfully 0, I should not have any loss. If it is negative, that's okay. If it is positive, I should be unhappy. If it's positive, I will take a rectified linear unit or a ReLU. So that means this red expression will be sum over dimensions max of 0 and uy d minus ux of d. You can verify that if I achieve true containment of actor in people, this quantity will go to 0, but if the red part sticks out, then I will pay with a loss. If actor is sticking out of people, then that results in a loss, area. Okay? Now, there are some asymmetries in this loss function. In particular, if I do not want x to be contained in y, then I actually want this violation. I actually want some part of the red type to stick out of the blue type, and I'll implement that by taking two ReLUs. I'll actually have a margin alpha, and I'll subtract the earlier ReLU from that. You can verify in exercises that this will give the desired behavior. This still does not recognize a certain asymmetry in the loss, because this is a sum over dimensions and that is also a sum over dimensions. Remember that in multiple dimensions, it's enough for the actor to violate its constraint in one dimension. It doesn't need to beat it in both dimensions. So if I want x to be a subtype of y, I want it to dominate. I want x to be contained. If it's not a subtype of y, it should violate in any one of the d dimensions. So there is an AND in this case. The violation, however, has an OR. So it can only violate in one of them. That's enough for me. So how do we implement that? If x is less than y, or x is a subtype of y, then for all dimensions d, we want uxd greater than or equal to uyd. And then we can implement L plus as the maximum. So over all the dimensions, what is the worst violation? Okay. Whereas if x is not supposed to be a subtype of d, then there has to exist some dimension where uxd is less than uyd. And that can be translated, you can verify it in exercises with this L minus expression over here. Okay. Now this scheme works, we have tested it, but it still has a limitation that these cones, if you will, are all upward open. We only characterize it by one corner, and then any vector above that corner is a member of that type. But this is a bit bad, because if I have people over here and I have politicians over there, it's true that politicians is contained in people, but the volume of them are both equally infinite, and that doesn't make sense, because the number of politicians is strictly less than the number of people, so less volume should be allocated to politicians than people. It's also hard to model negative correlation, because if you fan out enough in the positive orthant, everything overlaps. You cannot, for example, explicitly model that if x is a fruit, then x cannot be a scientist. For this reason, we are going to generalize from open cones to closed rectangles, and that will solve our problem. These rectangles will be in high dimension, d dimension, so we can call them hyperrectangles or boxes, box embeddings. Each type or item x will now be characterized by an interval for each dimension. So the item x or the type x will be identified by bxd and hxd, the base and the height of x in dimension d. Okay? And type to type containment will be characterized by interval containment in all dimensions. This is like laying out Venn diagrams using rectangles. Einstein, which may be a point, is contained in a rectangle called physicist, which in turn is contained in a rectangle called scientist. Angela Merkel is another physicist who is therefore also a scientist. George Bush is a politician but most decidedly not a scientist, and a banana is none of them. So, it is disjoint from all these. So, the question is, given a training type hierarchy like we are drawing in the very first slide, which gives us relations like x is a subtype of y or x is not a subtype of that y, can we train our bases and our heights or the upper corners? That is the optimization problem in fitting box embeddings.